There is a number written into the fabric of reality that should not exist. Not because it's strange or exotic, but because every equation we have says it should be 100 million billion times larger than it actually is. And if those equations had been right, the universe would have collapsed before a single atom ever formed. No stars, no planets, no you. The fact that you exist right now is, according to our best physics, essentially a mathematical miracle with no explanation. Tonight we're going to sit with that, the 50-year hunt, the moment Peter Higgs wept in a room full of scientists, and the quiet crisis that nobody talks about. Get comfortable, subscribe if you're new, because this one goes somewhere unexpected. Part 1. The Scream in the Equations. There is a number sitting inside the equations of physics right now, and it is wrong. Not wrong the way a student gets a test answer wrong, where you erase it and try again. Wrong in a way that should make the universe impossible. Wrong in a way that has kept the smartest people on the planet awake for decades, scratching at chalkboards and staring at computer screens, and quietly wondering whether everything we think we know about reality is missing something so fundamental that we don't even have the language to describe it yet. The number is 125 billion electron volts. That is the measured mass of the Higgs Boson, the particle discovered on July 4, 2012 at CERN's Large Hadron Collider in Geneva, Switzerland. And on the surface that number sounds perfectly reasonable. 125 billion electron volts. A little heavier than a hydrogen atom, nothing too alarming, the kind of number you'd write on a napkin and feel fine about. But here is the problem. When you actually sit down with the equations of quantum field theory, the most precisely tested framework in the history of science, and you ask those equations to predict what the Higgs mass should be, they do not give you 125 billion electron volts. They give you something closer to 10 million trillion billion electron volts. That is not a rounding error. That is not a measurement uncertainty. The equations, taken at face value, predict a Higgs boson roughly 100 million billion times heavier than the one we actually found. One followed by 17 zeros. A mismatch so enormous that it doesn't even feel like the same category of thing. Let me put that another way, because the numbers alone don't quite convey the absurdity here. Imagine you're trying to estimate the height of a house. A reasonable house, maybe 4 meters tall. Your best theory, your most precise mathematical framework comes back and tells you the house should be 480 trillion kilometers tall. Taller than the observable universe by a factor of several thousand. And yet when you walk outside and look at the house, there it is, 4 meters, sitting there calmly, looking perfectly normal. That is where we are with the Higgs boson right now. And the thing is, this isn't a case where physicists think the measurement might be off. The precision of the Higgs mass measurement is extraordinary. The uncertainty on that 125 billion electron volt figure is less than 1/10 of a billion electron volts. We know this number extraordinarily well. The measurement is not the problem. The problem is that the measurement disagrees with theoretical expectation by 17 orders of magnitude, and nothing in our deepest understanding of physics explains why. To really feel the weight of that, you need to understand what physicists mean when they use the word natural. In physics, natural doesn't mean organic or earthy. It means something very specific. A parameter in a theory is natural when you don't need to fine-tune it to an absurd degree to match observations. Natural parameters are ones that the mathematics kind of settles into on its own, without requiring a conspiracy of cancellations. When you have a natural theory, you can roughly estimate what values its parameters should take just from the structure of the equations themselves, and those rough estimates should be in the same ballpark as what experiments find. The Higgs mass is not natural, not even close. The equations predict that the Higgs mass should be enormous, and when you look at why they predict that, you run into something called quantum corrections, which are at the core of this whole crisis. Here is how quantum corrections work. In quantum field theory, nothing exists in isolation. Every particle is constantly interacting with the quantum vacuum around it, a seething, fluctuating background of virtual particles popping in and out of existence so briefly that you can never catch them directly, but whose effects are absolutely real and measurable. When you calculate the mass of a particle using quantum field theory, you don't just get the bare mass, the mass the particle would have if it existed in a perfect empty vacuum with no interactions. You get the bare mass plus contributions from every single virtual particle that the Higgs interacts with, even briefly, even transiently, even for an unmeasurably short moment. These contributions are called quantum corrections, and for most particles they're manageable. Electrons get quantum corrections, but those corrections are protected by a symmetry in the equations, a thing called chiral symmetry, which keeps them from spiraling out of control. Photons get quantum corrections too, but they're protected by gauge symmetry, the mathematical structure underlying electromagnetism. Protected particles have corrections that are at most logarithmic. They grow slowly, and they stay close to the particle's base mass. You never end up with a correction that dwarfs the thing it's correcting. The Higgs boson has no such protection. The Higgs is what physicists call a scalar particle. It has a quantum property called spin equal to zero, which makes it unique among the particles we've discovered. And that spin zero status is not just a curiosity. It has deep mathematical consequences. It means there is no symmetry in the standard model that protects the Higgs mass from quantum corrections. There is nothing in the equations that steps in and says, corrections, you can only grow this far. The corrections are instead quadratic divergences. They don't grow logarithmically and slowly. They grow proportional to the square of the energy scale at which new physics enters the picture. And if that energy scale is the Planck scale, the highest energy that makes sense in physics, around 10 to the power of 19 billion electron volts, then the corrections to the Higgs mass are enormous, staggeringly, universe-shatteringly enormous. So here is the situation you're left with. You have a bare Higgs mass, the starting value before corrections, which could in principle be anything. You have quantum corrections that push that mass up toward the Planck scale, and the observed mass is 125 billion electron volts. For these three things to be consistent, the bare mass and the quantum corrections must cancel each other with a precision of 1 part in 10 to the 17th. 17 decimal places of cancellation between two quantities that have no known reason to be related to each other in any way. Think about what that means in practice. Imagine you're trying to write down two numbers that, when added together, give you exactly 0.001. But each of those numbers, individually, is in the billions of billions. You need the first number to be something like 900 quadrillion, 322 trillion, 451 billion, 763 million, 209,847 point something. And the second number needs to be negative 900 quadrillion, 322 trillion, 451 billion, 763 million, 209,846.999. And somehow, with no mechanism, with no rule, with nothing in the theory requiring it, those two enormous numbers just happen to cancel to 17 decimal places. Every time. Exactly. For no reason. That is the hierarchy problem, and physicists find it so disturbing, not because it's mathematically impossible. It isn't. You can write down a theory where this cancellation just happens. It's technically allowed, but it is deeply, profoundly unnatural. And in the history of physics, when something has seemed this unnatural, it has almost always turned out to be a sign that the theory is incomplete, that something is missing, that there's a deeper structure hiding underneath that, once you find it, makes the cancellation obvious, either by explaining it or by showing why the question was framed wrong to begin with. Right now, we don't have that deeper structure. We've looked for it. Hard. We've built the biggest machine in human history to look for it, and we haven't found it, and that is why the equations are screaming. The central mystery here is not just mathematical. It touches something real, something that affects every atom in your body and every star in the sky. The Higgs mass is not just an obscure parameter in an abstract theory. It determines the stability of matter. It sets the scale for the whole universe. And the fact that it is the value it is, precisely, inexplicably, against all theoretical expectation, is either a cosmic coincidence, a clue to hidden physics we haven't discovered yet, or a sign that our deepest framework for understanding reality is missing something fundamental. That open question is where this whole story lives. And to really understand why it matters, we need to back up and ask a question that sounds almost embarrassingly basic, but turns out to be anything but. What is mass exactly? And why does it exist at all? Part 2, mass is the exception, not the rule. You've been carrying mass around your entire life, and probably never stopped to question whether it's actually the default state of things. It feels default. Everything has mass. You have mass. The ground has mass. The air has mass. Even the invisible gas molecules drifting around you right now have mass. It feels like mass is just the basic condition of matter, and the interesting question is how heavy things are, not whether they're heavy at all. But here is the thing that took physicists most of the 20th century to fully work out. Mass is not the default. Mass is the exception. In the universe as it exists at the deepest level, described by the equations of quantum field theory, particles don't automatically have mass just by existing. Mass is something that has to be acquired. It's a property that certain particles pick up through a specific interaction. An interaction with a field that permeates all of space, a field whose existence changes the rules for what matter can do. That field is the Higgs field, and understanding what the Higgs field actually is requires letting go of the intuition that particles are tiny solid balls floating through empty space. They're not. In quantum field theory, everything is a field. The electron isn't a little point of charge darting around the nucleus. It's an excitation in the electron field, a localized vibration in a quantum field that extends across the entire universe. The photon is an excitation in the electromagnetic field. The quarks inside your protons and neutrons are excitations in quark fields. Every fundamental particle we know is, at the deepest level, a ripple in its own underlying quantum field. The Higgs boson is a ripple in the Higgs field. And the Higgs field is special because unlike every other fundamental field we know, it has a non-zero value in empty space. This is the crucial point. Everywhere in the universe, in the empty space between galaxies, in the space between atoms, in the space between your fingers, the Higgs field is not zero. It has what physicists call a vacuum expectation value, a background level of about 246 billion electron volts that it settles into even when there are no particles around. That might sound technical, but the physical consequence is enormous. Because other quantum fields interact with the Higgs field, and when a particle moves through space, it is constantly pushing through this background Higgs field. And that resistance, that constant interaction with the omnipresent Higgs field, is what we experience as mass. The stronger a particle interacts with the Higgs field, the more resistance it encounters, the harder it is to accelerate. The harder it is to accelerate, the more massive it seems. Mass isn't a thing the particle carries around inside itself. Mass is a relationship between the particle and the field it's swimming through. If you could somehow switch off the Higgs field, zero it out across all of space, every particle that gets its mass from the Higgs would instantly become massless. They would all begin travelling at the speed of light, because in the absence of mass, that's what relativistic particles do. This is why the photon is massless. The photon doesn't interact with the Higgs field at all. It doesn't couple to it, it doesn't feel it, it passes right through that ubiquitous background without any interaction. No interaction, no resistance, no mass. The photon has been flying at the speed of light since the moment it was created, and it will continue doing so until it is absorbed, because nothing about the Higgs field slows it down. Same story for the gluon, the carrier of the strong nuclear force. No Higgs interaction, no mass. But the W and Z bosons, the carriers of the weak nuclear force, interact with the Higgs field very strongly, and they are heavy. The W boson is about 80 billion electron volts. The Z boson is about 91 billion electron volts, almost as heavy as an entire gold atom's nucleus. Compared to the photon, which has zero mass, the W and Z are enormously massive particles, and that mass comes entirely from their strong coupling to the Higgs field. The top quark, the heaviest known fundamental particle at about 173 billion electron volts, couples to the Higgs field more strongly than any other known particle. The electron, which is about 500,000 electron volts, couples to the Higgs field weakly. The neutrinos, which have masses so small we still can barely measure them, barely interact with the Higgs field at all. Every particle's mass is a fingerprint of how much it talks to the Higgs. And here is where it gets even more interesting, because all of this depends on something that happened at the very beginning. In the first tiny fractions of a second after the Big Bang, we're talking about 10 to the power of negative 12 seconds, 1/trillionth of a second after the universe began, the Higgs field underwent what physicists call electroweak symmetry breaking. Before that transition, the Higgs field had a zero expectation value. The universe was so hot and energetic that the Higgs field was fluctuating too violently to settle into its current stable background value. And in those first moments before the transition, every particle was effectively massless. The photon, the W boson, the electron, the quarks, all massless, all racing around at the speed of light in a hot, dense soup of undifferentiated energy. Then the universe cooled, and as it cooled, the Higgs field found its lowest energy state, not at zero, but at that non-zero vacuum expectation value of 246 billion electron volts. The field settled, the background switched on, and in that instant every particle that interacted with the Higgs field suddenly acquired mass. The universe went from a featureless blur of massless particles to a place where things could slow down, clump together, form bound states, and eventually, after hundreds of millions of years, form atoms, stars, planets, and us. The Higgs field is not just background physics trivia, it is the reason structure exists at all. But here is the connection that brings all of this back to the central crisis. The Higgs field explains how particles get mass. It tells you the mechanism. What it does not tell you is why the field settled where it did, why the vacuum expectation value is 246 billion electron volts and not something vastly larger. And because the Higgs boson is the excitation of that field, the ripple you create when you disturb it, the mass of the Higgs boson reflects the properties of the field itself. A very heavy Higgs would mean a very different field configuration, a very different vacuum, a very different universe. The specific mass of the Higgs boson, 125 billion electron volts, is what sets the scale for all of this. It's not just a number in a table of particle properties, it is the number that determines whether the Higgs field settles into a stable, life-permitting configuration or something else entirely. And the fact that this number requires 17 decimal places of unexplained cancellation to come out right is not a secondary technical concern. It is the core problem. It is the screaming in the equations. Before we can fully grapple with that problem, though, we need to understand how we know any of this at all. Because the Higgs field is invisible. You can't see it, feel it, measure it directly. The only way to study it is to disturb it, to pump enough energy into a small region of space that you shake loose an actual excitation of the field, a real Higgs boson that you can then detect and measure. And the machine that finally did that, after 50 years of waiting, is one of the most remarkable engineering achievements in human history. Part 3. The particle that took 50 years. In 1964, several groups of physicists independently published papers proposing the same basic idea, and those papers changed the direction of physics for the next 5 decades. The problem they were solving sounds almost philosophical. In the early 1960s, the theoretical framework for particle physics was in a strange condition. Physicists had equations that described particles and forces with astonishing mathematical elegance. But those equations required particles to be massless to preserve the mathematical symmetries the theory was built on. The symmetries were gauge symmetries, and gauge symmetries are beautiful and powerful, but they seem to forbid particle masses. Every time you tried to add mass to particles in a gauge symmetric theory, the math broke down. You got nonsensical results, infinite probabilities, unphysical predictions. And yet obviously particles had mass. You could hold them, weigh them, send them through magnetic fields and watch them curve. The universe clearly had massive particles. The W and Z bosons, which hadn't been discovered yet but were theoretically required by the emerging picture of the weak force, had to be heavy. So something was wrong with the logic that said gauge symmetry forbids mass. Peter Higgs, working at the University of Edinburgh, along with Robert Brute and Francois Engler working in Brussels, and separately Gerald Guralnick, Carl Hagen, and Tom Kibble working in London, realised that you could have massive particles and preserve gauge symmetry at the same time if you introduced a new field, a scalar field, a field that pervades all of space, settles into a non-zero background value, and couples to other fields in just the right way. When a gauge boson tries to move through this background field, it picks up mass not by violating the symmetry, but by eating it, absorbing a component of the Higgs field itself and converting it into longitudinal polarization, which is the physical hallmark of a massive particle. This mechanism, now called the Brute-Englert-Higgs mechanism, not only gave particles mass in a mathematically consistent way, it also made a specific prediction. If this scalar field exists, and if it spontaneously breaks the electroweak symmetry, then there should be a leftover excitation of the field, a particle, the Higgs boson. The theory predicted this particle with extraordinary specificity. It should be electrically neutral. It should have spin zero, making it the only known fundamental scalar. It should couple to other particles in proportion to their masses, meaning it talks most strongly to the heaviest particles. Everything about its behavior was predicted in detail. Everything except its mass. The mass of the Higgs boson wasn't something the theory could predict from first principles. It was a free parameter. It could, in principle, be anywhere from a few billion electron volts to the Planck scale. Finding it required building a machine that could probe energy scales high enough to actually produce a Higgs boson, to smash particles together with enough collision energy to shake loose an excitation of the Higgs field. And that was a problem, because in 1964, no such machine existed. The particle accelerators of the era could reach energies of a few billion electron volts. If the Higgs boson happened to be light enough, they might have found it. It wasn't. The decades passed. Colliders got bigger and more powerful. The Tevatron at Fermilab in Illinois, the most powerful accelerator in the world for much of the 1980s and 90s, reached energies of almost 2 trillion electron volts. It didn't find the Higgs either, though it narrowed the possible mass range considerably. The LEP collider at CERN ran through the 1990s and pushed the lower bound on the Higgs mass above about 114 billion electron volts. And still, nothing. The physics community had been waiting for this particle for 35, 40, 45 years. Entire careers had been built around theories that assumed its existence. The whole standard model, the complete framework for particle physics that had been assembled over the decades, depended on the Higgs mechanism being real. Without it, the W and Z bosons had no mass. The weak force didn't work, matter as we know it didn't make sense. The Higgs boson wasn't just an interesting particle to find, it was the linchpin, the keystone, the last piece that the whole architecture required. The Large Hadron Collider was built in large part to find it, 27 kilometers in circumference, buried roughly 100 meters underground in a ring straddling the border between Switzerland and France near Geneva. 2,000 magnets, many of them superconducting, cooled to temperatures colder than outer space, 1.9 degrees above absolute zero, generating magnetic fields strong enough to bend beams of protons moving at 99.99999% of the speed of light. 2 beams travelling in opposite directions around the ring, steered into head-on collisions at 4 points around the circumference, where the huge detectors, Atlas and CMS, each one roughly the size of a 5-story building and weighing tens of thousands of tons, sat waiting to catch the debris. The LHC turned on in September 2008. Then a faulty electrical connection between 2 of the superconducting magnets caused an explosion that damaged a significant section of the tunnel, and the machine shut down for over a year. When it restarted, it did so at lower energies than planned. The first run, from 2010 to 2012, reached collision energies of up to 8 trillion electron volts. Still enough, as it turned out. July 4th, 2012, CERN, Geneva, an auditorium packed beyond capacity. Peter Higgs himself was in the room, now 83 years old, having waited 48 years to see whether the particle he'd helped predict actually existed. Rolf Dieter Hoyer, CERN's Director General at the time, opened the proceedings. Then the results from Atlas came up. Then the results from CMS. Both detectors, independently, had found a new particle consistent with the standard model Higgs boson, at a mass of approximately 125 billion electron volts. The statistical significance was more than 5 standard deviations, the gold standard in particle physics for claiming a discovery, representing odds against a random fluctuation of roughly 1 in 3.5 million. The room erupted. Peter Higgs wiped tears from his eyes. It was by any measure one of the greatest experimental confirmations in the history of science. 50 years after the theoretical prediction, the particle was real, the Higgs boson existed, the mechanism was confirmed, the standard model was complete. But here is the thing about completing the standard model. The moment you find the Higgs, you can measure its mass precisely, and the moment you measure its mass precisely, you can plug that number back into the equations of quantum field theory and ask whether it's natural, whether it makes sense, whether the theory can explain it. And the answer that came back was no. The discovery didn't close a problem. It opened the deepest one in physics, because at 125 billion electron volts, the Higgs mass is sitting right in the range where the hierarchy problem is as bad as it can possibly be, light enough that the standard model works, but small enough that the quantum corrections are completely out of control. The Nobel Committee awarded the prize to Peter Higgs and François Englert in 2013 for predicting the particle. The physics community celebrated, and then, quietly, everyone went back to their calculations and realized that the answer they'd been waiting 50 years for had come with a problem attached. The particle that completed physics also broke it. Part 4, the quiet problem that walked in. The discovery of the Higgs boson didn't arrive in a vacuum, if you'll excuse the pun. The hierarchy problem, the gap between the measured and theoretically expected Higgs mass, had been known as a theoretical issue since at least the 1970s. Physicists like Leonard Susskind and Martinus Veltman had written about it. They'd identified it clearly, given it a name, and pointed out that it was deeply unsatisfying, but as long as the Higgs boson hadn't been found, you could tell yourself that maybe the mass would turn out to be large, near the TV scale, and that the natural theories being developed would turn out to explain it. Finding the Higgs at 125 billion electron volts removed that escape route. The problem was no longer theoretical, it was experimental. To really understand why the hierarchy problem is so severe, you need to understand something particular about spin-zero particles. This is where the Higgs boson's scalar nature, its spin of zero, becomes the crux of the whole issue. In quantum field theory, the spin of a particle is not just an intrinsic quantum number like a label. It has profound mathematical consequences for what kinds of symmetries can protect the particle's mass from quantum corrections. Let's compare 3 cases that make this very concrete. Consider the photon first. The photon has spin 1 and is the carrier of electromagnetism, which is governed by a gauge symmetry called U1. This gauge symmetry is not just an aesthetic feature of the theory. It is mathematically enforced in such a way that the photon must remain massless. If you tried to write down a quantum correction to the photon mass, the correction would violate gauge invariance, and the theory would become internally inconsistent. So the gauge symmetry literally prevents the photon mass from getting corrections. It acts as a mathematical guardian. The photon is exactly massless, not approximately massless, not massless, unless you include higher order corrections, exactly zero, protected. Now consider the electron. The electron has spin 1/2, making it a fermion. Fermions are protected by a symmetry called chiral symmetry. When the electron is massless, the theory has an exact symmetry between left-handed and right-handed versions of the electron. This symmetry is broken by the electron's mass, but crucially, breaking it costs energy proportional to the mass itself. This means that quantum corrections to the electron mass can't be dramatically larger than the electron mass. If the electron were massless, the corrections would be exactly zero, because the symmetry would be exact. When you give the electron a small mass, you break the symmetry slightly, and the corrections are proportional to that small mass. The corrections can only be logarithmically large, not power law large. The electron's small mass is technically natural because there's a symmetry, chiral symmetry, that would be restored if the mass was zero. The Higgs boson has spin zero. It is a scalar. And here is the painful truth about scalars. There is no symmetry in the standard model that would be enhanced or restored if the Higgs mass was zero. The Higgs mass breaks no symmetry by being small, which means there is nothing, no mathematical structure, no conservation law, no symmetry principle that protects the Higgs mass from getting large quantum corrections. And large they are. Every particle that interacts with the Higgs field contributes a quantum correction to the Higgs mass. You can draw these contributions as Feynman diagrams, loop diagrams, where a virtual particle-antiparticle pair pops out of the vacuum, interacts with the Higgs, and then annihilates. Each such loop contributes a correction proportional to the square of the mass of the particle running in the loop. And unlike electron corrections to the photon, which are suppressed by the gauge symmetry, these corrections to the Higgs mass are quadratically divergent. They grow as the square of whatever energy scale you integrate up to. If you integrate up to the Planck scale, 10 to the power of 19 billion electron volts, each heavy particle contributes a correction of roughly that scale squared. The worst offender is the top quark. At 173 billion electron volts, the top quark is by far the heaviest of the 6 quarks and the heaviest of all the fermions. Its coupling to the Higgs field is proportional to its mass, which means it talks to the Higgs field more strongly than any other particle. and when you compute the one-loop correction to the Higgs mass from top quark loops, you get a contribution that's roughly negative 3 times the square of the top quark mass divided by 8 pi squared, multiplied by the square of whatever energy cutoff you use. Plug in the Planck scale as your cutoff, and this single correction alone is something like 10 to the 38 billion electron volts squared in magnitude. The observed Higgs mass squared is roughly 10 to the 4 billion electron volts squared. The correction from the top quark alone is 34 orders of magnitude larger than the quantity it's correcting, and the top quark isn't alone. The W and Z bosons contribute their own loops. The Higgs boson contributes loops to its own mass through self-interactions. Every particle in the standard model that couples to the Higgs, directly or indirectly, contributes. The corrections pile on. And they all need to cancel with the bare Higgs mass to give the observed value of 125 billion electron volts. Here is the thing that physicists emphasize when they explain why this is considered such a crisis. The calculation itself is perfectly well defined. There's no mistake in it. You're not doing the math wrong when you get these enormous numbers. Quantum field theory, renormalization theory, these are extraordinarily well-tested tools. The calculation is telling you something real about the structure of the equations. What it's telling you is that the observed Higgs mass is the result of a conspiracy between 2 enormous quantities, the bare mass and the sum of all corrections, that almost perfectly cancel. The word almost is doing enormous work in that sentence, because almost here means to 1 part in 10 to the 17th, which is not almost at all. That is an exact cancellation to 17 decimal places, presented as if it's a coincidence. The naturalness principle in physics is the intuition, born from decades of successful theory building, that when you see a parameter that requires extreme fine-tuning to match observations, you should look for a deeper explanation. The reason physicists trust this intuition is that it has worked before. When you see a number that looks unnaturally small or unnaturally large, it usually means there's a symmetry or a mechanism you haven't found yet that actually explains the value. Naturalness is not a law. It's not a theorem. It's a heuristic. But it's a heuristic with an extraordinary track record, and the Higgs mass violates it spectacularly. The question isn't whether the standard model can technically accommodate the Higgs mass by setting the bare mass to just the right value. It can. You just adjust the bare mass parameter by hand until the sum works out. The question is whether a universe described by the standard model and nothing else, no additional physics, no new particles, no deeper structure beyond what we've found, would produce a Higgs mass of 125 billion electron volts for any reason that makes sense. And the answer is no. Not in any natural way. Not without an extraordinary coincidence that the theory provides no mechanism for. The hierarchy problem is not, we can't write down the right number. It's, we can write down the right number, but we have to put it in by hand, and the theory gives us no reason to expect it to stay there. It's not that the math doesn't work. It's that the math works only if you allow it to be grotesquely fine-tuned, and fine-tuning without explanation is, to most physicists, a sign that something is wrong. The LHC ran, the Higgs was found, the mass was measured with extraordinary precision, and the hierarchy problem walked quietly into the room and sat down, uninvited but impossible to ignore. Now here is the really existential part. This is not just an abstract mathematical discomfort. The specific value of the Higgs mass has direct physical consequences for whether the universe can exist at all. If the Higgs had taken its natural large value, if the cancellations hadn't happened, if the bare mass and corrections hadn't conspired to give 125 billion electron volts, the universe we inhabit would not have survived its first moment. Let's go there. Part 5. The avalanche of quantum corrections. The quantum vacuum is not empty. This is one of those statements in physics that sounds like poetry, but is actually just a description of what the mathematics tells us. At every point in space, at every moment in time, there is a ceaseless churning activity of virtual particles, pairs of particles and antiparticles that flicker in and out of existence so briefly that they can never be directly observed, but whose collective effect on real particles is absolutely measurable. The Casimir effect, Lamb shift in hydrogen spectral lines, vacuum polarization of electromagnetic fields, all of these are experimental signatures of the quantum vacuum's activity, measured to extraordinary precision and matching quantum field theory predictions exactly. The quantum vacuum is real, and the Higgs boson lives in it, subject to all of its churning. When quantum field theorists compute the mass of the Higgs boson from first principles, what they're really doing is calculating how the Higgs behaves in this quantum vacuum. They're asking, given all the ways the Higgs can interact with all the other fields in the theory, and given that the vacuum is not empty but filled with virtual fluctuations of all those fields, what is the energy cost of having a Higgs particle sitting there? That energy cost is what we call mass. The mathematical tool for doing this calculation is the Feynman diagram. You draw a picture of the Higgs propagating through space, and then you draw all the ways virtual particles can affect that propagation. The simplest diagrams are the most important. There's a diagram where a top quark and a top antiquark pop out of the vacuum, each interact with the Higgs line, and then annihilate back into nothing. This is a one-loop diagram, one closed loop of virtual particles. There's another diagram where a pair of W bosons do the same thing, another with Z bosons, another with the Higgs itself, looping back on its own propagator. Each diagram contributes an additive correction to the Higgs mass squared. What makes this different from, say, corrections to the electron mass is the quadratic divergence. For the electron, if you try to calculate the quantum correction, you find that the integral over virtual momenta converges after you include the electron's mass as a regulator. The correction is of order the electron mass times logarithms. It's finite and proportional to what you started with. Good behavior, protected by chiral symmetry. For the Higgs, the integral over virtual momenta does not converge in this way. If you just try to compute the correction naively, you get an integral that diverges quadratically. It grows as the square of the maximum momentum you include. In a sense, contributions from very high-energy virtual particles don't automatically become small and negligible. They keep adding up, and each increment of energy you include in your calculation adds a proportional correction to the Higgs mass squared. The way physicists handle this is with a regularization scheme. You introduce a cutoff energy, call it lambda, and say, we'll only include virtual particles with momenta below lambda. This is an honest procedure, because there's always a physical justification. At some energy scale, the standard model surely breaks down and new physics enters. Above that scale, you can't use standard model loops anyway. The cutoff represents the scale at which something new happens. But here's the problem. The correction to the Higgs mass squared is proportional to lambda squared. It grows as the square of the new physics scale. And the hierarchy problem is precisely the question. Why is the scale of new physics so far above the Higgs mass? If new physics enters at, say, 1,000 times the Higgs mass, the TV scale, then the corrections are about 1,000,000 times the Higgs mass squared. Already bad. If new physics doesn't enter until the Planck scale, about 10 to the 17 times the Higgs mass, the corrections are about 10 to the 34 times the Higgs mass squared. You need the bare Higgs mass squared to cancel these corrections, digit by digit, to leave behind the observed value of roughly 15,000 billion electron volts squared. The top quark is the single most important contributor to this problem, and it's worth dwelling on why. The coupling of the Higgs to the top quark is the Yukawa coupling, and for the top quark this coupling is approximately equal to 1, its order unity, the largest it could reasonably be. Other quarks have Yukawa couplings of 100th or 1000th, or even smaller. The top quark's coupling is huge, and since the correction to the Higgs mass from a fermion loop is proportional to the square of the Yukawa coupling times the square of the cutoff, the top quark absolutely dominates the hierarchy problem. You can think of it this way. The top quark is constantly popping into existence as a virtual pair. Top quark plus top antiquark, somewhere near the Higgs propagator. Each such pair briefly borrows the Higgs field energy, contributes to the effective Higgs mass, and then disappears. The pairs are heavy, about 173 billion electron volts each, and the contribution they make is roughly proportional to their mass squared. Multiplied by the loop factor and the Yukawa coupling, and integrated over all momenta up to the cutoff, you get a correction that at the TV scale alone is already about 10 times the observed Higgs mass squared. At the Planck scale, you can stop counting decimal places. The W and Z bosons add their own corrections through gauge boson loops. These corrections are also quadratically divergent, though they're somewhat smaller than the top quark contribution, simply because the gauge couplings are less than 1. The Higgs quartic self-coupling, the Higgs talking to itself, also contributes a loop correction. Even quarks other than the top contribute. though their effects are smaller. All of these corrections pile on top of each other. They come with different signs. Fermion loops and boson loops contribute corrections with opposite signs, a hint at what supersymmetry will later exploit, but with generic sizes that are vastly larger than the observed Higgs mass. Here is the analogy that I think captures the spirit of the problem most clearly. Imagine you're a budgeter for a program with a running total that must stay exactly between $0 and $1. Every single day, thousands of independent adjustments come in, each one randomly chosen from -$10 billion to +$10 billion. The adjustments don't know about each other. They're generated by completely different processes, and yet somehow, every single day when you add them all up, the total stays in that $0 to $1 range. Not because someone is managing it, not because there's a rule that forces it, it just happens, every day, to the required precision. That is the Higgs mass problem. What would make this natural? What would make physicists feel like the theory was explaining something, rather than requiring an absurd coincidence? A mechanism that links the corrections to each other, that forces them to cancel for a reason. A symmetry that would make the bare mass small in the same way that chiral symmetry makes the electron mass technically natural. Some structure that says, of course these corrections cancel, because they have to, because there's a deeper principle requiring it. Physicists thought they had found such a principle. They thought it was called supersymmetry. They were almost certain it would show up at the LHC. It would solve the hierarchy problem elegantly, beautifully, completely. It didn't show up. But before we get to that, we need to follow the logic to its most extreme conclusion. Because the hierarchy problem isn't just about mathematical aesthetics, it's about whether the universe survives. Part 6. The cancellation that shouldn't work. Let's be very explicit about the numbers, because I think people hear fine-tuning and imagine something like choosing between 9 and 11 when you expected 10. The actual numbers here are so extreme that they deserve to be stated plainly. The observed Higgs mass squared is approximately 1.6 times 10 to the 4 billion electron volts squared. That's the target. That's what the theory has to produce after all corrections are accounted for. The correction from top quark loops, computed at one loop in the standard model and integrating up to the Planck scale, is approximately negative 6.4 times the square of the top quark mass times lambda squared divided by 16 pi squared. When you plug in the top quark mass and the Planck scale, this single correction comes out to roughly negative 10 to the 38 billion electron volts squared. The target is 10 to the 4. The correction is 10 to the 38. The ratio is 10 to the 34. To get from 10 to the 38 down to 10 to the 4, you need a cancellation across 34 orders of magnitude between the bare mass term and the quantum corrections. Let me try to convey the magnitude of that cancellation differently. 34 orders of magnitude is not like saying you need to balance a seesaw. It's more like this. Take the distance from the Earth to the edge of the observable universe, roughly 46 billion light-years, or about 4 times 10 to the 26 meters. Now express that distance in the smallest unit of length that makes physical sense. The Planck length, about 1.6 times 10 to the minus 35 meters. The ratio of the observable universe's diameter to the Planck length is about 2.8 times 10 to the 61. The hierarchy problem's fine-tuning is less extreme than that, but it's in the same conceptual territory. You're asking for a cancellation between two quantities whose ratio to each other is comparable to the ratio of cosmic to quantum scales. And unlike that ratio, which has a physical explanation, the universe is old and expanded a lot. The fine-tuning of the Higgs mass has no known physical explanation. None. The term physicists use for a quantity that requires this kind of tuning is unnatural, and the distinction between natural and unnatural parameters is not arbitrary. Consider by contrast the smallness of the electron mass. The electron is 453,000 electron volts. The Higgs is 125 billion electron volts, so the electron is about 275,000 times lighter than the Higgs. Is the electron's small mass unnatural? Is it also a hierarchy problem? The answer is no, and the reason tells you everything about why the Higgs problem is special. As we discussed, the electron's mass is technically natural because of chiral symmetry. The corrections to the electron mass are proportional to the electron mass itself. Specifically, they're the electron mass times logarithms of ratios of scales, which can be large but are never catastrophically large. The electron's small mass doesn't require a cancellation between huge numbers. It just requires the electron's Yukawa coupling to the Higgs to be small, and that small coupling is stable under quantum corrections. You can start with a small electron mass, and quantum corrections will leave it roughly small. Now try the same logic for the Higgs. You want to start with a small Higgs mass. But unlike the electron, whose corrections are proportional to its own mass, the Higgs corrections are proportional to lambda squared, to the scale of new physics, completely independent of the Higgs mass itself. So starting with a small bare Higgs mass doesn't help. The corrections drive it up to lambda regardless of where you start. You have to keep adjusting the bare mass order by order in perturbation theory to keep the physical mass small. And those adjustments get more and more extreme as you push the theory to higher energies. It's not like balancing a ball on a level table, it's like trying to balance a ball on a slope. You have to keep pushing it back, harder and harder, as you try to go higher. This is what physicists mean by saying the Higgs mass is unstable to radiative corrections. It wants to run away to large values. Keeping it small requires active, ongoing, precise intervention in the form of fine-tuned bare mass parameters, and a theory that requires this kind of intervention, with no mechanism justifying it, is widely considered to be an incomplete description of nature. The philosophical discomfort here is not just aesthetic, though it is also aesthetic. When physicists look at a fine-tuned theory, they feel what you might feel if you saw an impossibly tall stack of coins balanced perfectly on a single point. Not just one coin, but thousands, each one perfectly placed. You can do it. It's not physically impossible, but you immediately wonder who placed them there and why, and whether they're about to fall. The naturalness principle is the intuition that says, this kind of extraordinary balance doesn't just happen. Something is maintaining it. Find the mechanism. In the history of physics, this intuition has paid off repeatedly. The small mass of the kaon, the strange meson, looked suspiciously fine-tuned in the 1960s. It wasn't explained by anything in the theory of the time. Finding the explanation required predicting the existence of the charm quark, which was later discovered. The smallness of certain coupling constants in quantum chromodynamics was explained by asymptotic freedom. Naturalness concerns led to the prediction of the top quark mass range before it was measured. The intuition works, and right now the intuition is screaming about the Higgs. The fine-tuning of the Higgs mass is the most extreme case of an unnatural parameter in the standard model. It dwarfs other fine-tuning concerns. It sits there, 17 decimal places of unexplained cancellation, quietly defying the entire framework of how physics is supposed to work. Now. You've been patient with the mathematics, and I want to pay that patience back with the really terrifying part. What happens if the cancellation doesn't happen? What if, in some other universe, or in the moments after our own Big Bang, the Higgs mass had taken a value closer to what the equations naturally predict? Part 7, a universe that never made it. Let's follow the logic of a heavier Higgs boson, because the consequences unfold fast. Shockingly, violently fast. We're talking about events occurring in fractions of a second. The universe began, as best we can tell, in an extraordinarily hot, dense state. In the first instance after the Big Bang, the energy density was so enormous that all particles were effectively massless, because the temperature was above the electroweak symmetry breaking scale. The Higgs field hadn't yet settled into its non-zero vacuum expectation value. Everything was a hot plasma of undifferentiated energy, expanding and cooling. Then, at roughly 10 to the power of negative 12 seconds, 1/trillionth of a second, the temperature dropped below the electroweak transition temperature. The Higgs field underwent symmetry breaking. It settled into its vacuum configuration. Particles acquired mass. The W and Z bosons became heavy. The quarks picked up mass. The whole structure of particle physics as we know it clicked into place. This transition is called the electroweak phase transition, and everything that follows, protons, neutrons, atoms, stars, you, depends on this transition going a specific way, with the Higgs field settling into a specific vacuum configuration that gives particles specific masses. Now ask what would have happened if the Higgs mass had been much larger. Say, anywhere near the scale suggested by the quantum corrections, 1 trillion billion electron volts or more close to the Planck scale. A heavier Higgs boson means a steeper potential energy curve for the Higgs field. The field still undergoes symmetry breaking, still settles into a non-zero vacuum expectation value, but that vacuum expectation value would be wildly different. much larger, and the masses of all the particles that couple to the Higgs would scale with it. The W and Z bosons, whose masses are proportional to the Higgs vacuum expectation value, would be fantastically heavy. The top quark, whose mass is proportional to its Yukawa coupling times the vacuum expectation value, would be even heavier than it already is. Every particle's mass would be inflated by the change in the Higgs field's vacuum configuration. What does a universe full of much heavier particles look like? It looks like a universe that collapses almost immediately. Here's why. When particles are heavier, they carry more energy. When the universe is full of high-energy, heavy particles, the energy density of the early universe is higher than in our case. A higher energy density means stronger gravitational attraction. And in the very early universe, the competition between the expansion rate, driven by the initial conditions of the Big Bang, and the gravitational attraction trying to pull everything back together is extraordinarily delicate. In our universe, the expansion won. Just barely. With inflated particle masses, there's more gravity. The gravitational pull overwhelms the expansion. The universe, instead of expanding and cooling and eventually forming structure, reaches a maximum size and then collapses back in on itself. A big crunch. All of this happening before a microsecond has elapsed, before any protons have formed, before any neutrons, before any nuclei, before any atoms, before any molecules or chemistry or biology. Just a brief flicker of enormous energy followed by total collapse. Now you might wonder, does the Higgs mass have to be exactly what it is for this to work out? Or is there some range? The answer is that there is a range, but it's tight. Models of universe formation suggest that if the Higgs mass were even a few orders of magnitude larger than it is, the electroweak vacuum configuration would shift enough to send most particles into a drastically different mass regime, one incompatible with the formation of stable protons and neutrons. The universe's capacity to form atoms depends on protons and electrons having a very specific mass ratio. If the proton mass changes substantially because the quark masses change, the whole chemistry of the universe destabilizes. Atoms as we know them require the electromagnetic scale to be close to what it is, and that scale is set by the Higgs. A factor of 10 different. The universe might still produce some kind of matter, though likely not hydrogen chemistry. A factor of 1,000. Almost certainly a universe without stable atoms. A factor of 10 to the 17, the natural Higgs mass. The universe probably doesn't last a picosecond. The Higgs mass at 125 billion electron volts is not just the value we measured. It is within some range the value that makes the universe we live in possible, and the explanation for why it takes this life-permitting value, the fine-tuning, the cancellation to 17 decimal places, points either toward undiscovered physics that enforces this cancellation for a reason, or toward something far more philosophically discomforting. And physicists thought for several decades that they knew what the physics was. They had a theory. It was called supersymmetry. It was elegant. It was predicted to show up at exactly the energies the LHC would probe. It was, many thought, essentially certain to be confirmed. It wasn't. Part 8. The answer that never arrived. Supersymmetry arrived in theoretical physics in the early 1970s, like the answer to a prayer that the physicists hadn't quite finished composing yet. The core idea of supersymmetry, SUSY, as it's known, is a symmetry between fermions and bosons, between particles with half-integer spin, the matter particles like quarks and electrons, and particles with integer spin, the force carriers, like photons and gluons and the Higgs. Supersymmetry proposes that for every particle we know, there exists a superpartner particle with the same mass, same charge, same interactions, but differing in spin by 1/2. The superpartner of the electron is the selectron, a boson. The superpartner of the photon is the photino, a fermion. The superpartner of the quarks are the squarks. The superpartner of the gluon is the gluino. The superpartner of the Higgs bosons are the Higgsinos, and vice versa. And here is why this is a potential solution to the hierarchy problem. Remember the structure of the quantum corrections to the Higgs mass. Fermion loops contribute corrections with a negative sign. Boson loops contribute corrections with a positive sign. In the standard model, these contributions don't cancel because the fermions and bosons have different masses and different couplings. The top quark loop is huge and negative. There's no boson in the standard model with the right properties to cancel it. But if supersymmetry were exact, if every particle had an exact superpartner with exactly the same mass, then the fermion loop corrections would be exactly cancelled by the corresponding boson loop corrections. The top quark loop would be cancelled by the stop squawk loop. The gauge boson loops would be cancelled by the corresponding Gauguino loops. The quadratic divergences would disappear completely, not because of a coincidence, but because of a symmetry that enforces the cancellation. The Higgs mass would be naturally small, protected by supersymmetry in the same way the photon mass is protected by gauge symmetry. It's an extraordinarily elegant solution, and supersymmetry comes with additional attractions. It provides a natural candidate for dark matter. The lightest supersymmetric particle would be stable and interact only weakly with ordinary matter, exactly the properties needed. It allows the three force coupling constants of the standard model, for the strong force, weak force, and electromagnetism, to unify to a single value at very high energies, suggesting an underlying grand unified theory. And it arises naturally in string theory, which is the most developed candidate for a quantum theory of gravity. For roughly 30 years, from the mid-1970s through the first decade of the 2000s, supersymmetry was the dominant paradigm for physics beyond the standard model. It was not just popular, it was considered by many physicists to be essentially inevitable. The hierarchy problem was real and severe, SUSY solved it, and SUSY predicted superpartners at energy scales within reach of the LHC. The logic seemed airtight. The crucial prediction was this: for supersymmetry to solve the hierarchy problem naturally, without reintroducing fine-tuning, the superpartners responsible for cancelling the top quark loops had to be not too much heavier than the top quark itself. The stop squawk, in particular, should have a mass in the range of a few hundred billion electron volts to maybe 1,000 billion electron volts, the TV scale. If the stop squawk were too much heavier than that, it would cancel the top loop, yes, but only partially, and you'd be left with a residual correction that still required fine-tuning to cancel. Natural supersymmetry meant light stops. The LHC was designed in part to find these particles. When it turned on in 2010 and began producing proton-proton collisions, the ATLAS and CMS experiments set about searching for the signatures of supersymmetric particles, events with missing energy from escaping neutralinos, events with many high-energy jets from squawk and gluino production, events with displaced vertices from long-lived sparticles. Nothing. The LHC ran through 2012, no superpartners. Then through 2015, still no superpartners. Through 2018, nothing. The LHC restarted at higher energies in 2022 and continued through its third run. As of the time I'm speaking to you, no supersymmetric particles have been found. The exclusion limits are now severe. Gluinos, the superpartners of gluons, are excluded below masses of about 2,300 billion electron volts. Squawks are excluded below about 1,800 billion electron volts for the lightest generations. Stop squawks, the critical players for solving the hierarchy problem, are excluded below about 1,200 to 1,500 billion electron volts, depending on the decay mode and assumptions about the lightest supersymmetric particle. These limits don't rule out supersymmetry as a mathematical theory. You can always push the superpartners to higher masses and the theory remains internally consistent. But every time you push the stops heavier, you make the hierarchy problem worse. If the stop is at 1,200 billion electron volts instead of 300, the cancellation is less efficient, and you need more fine-tuning to get the Higgs mass right. At this point, natural SUSY, the version that actually solves the hierarchy problem without reintroducing fine-tuning, is either dead or dying. Physicists have proposed modifications, split supersymmetry, where only some superpartners are light, but that requires its own tuning. High-scale supersymmetry, where the superpartner masses are pushed to much higher energies, but that provides no protection for the Higgs mass and doesn't solve the hierarchy problem. There are variations and complications and model-building attempts. But the clean, elegant, natural supersymmetry that was supposed to show up at the TV scale and explain everything, that picture is in serious trouble. The alternatives that were always acknowledged as theoretical possibilities but considered unlikely. Composite Higgs models, where the Higgs is not a fundamental particle, but a bound state of more elementary constituents. Extra dimensions of space that dilute the hierarchy problem geometrically. Technicolor theories, where a new, strong force dynamically generates the electroweak scale. These have also not found experimental confirmation. The Higgs boson was found where the naturalness arguments about supersymmetry suggested it should be around 125 billion electron volts in the natural SUSY range. But the superpartners that were supposed to explain why it's there haven't been found. The solution that was supposed to make everything make sense hasn't appeared, which leaves physics in a peculiar and uncomfortable position. We have a beautifully precise measurement of a number that is extraordinarily unnatural. We have elegant theories that should explain it, which haven't been confirmed. And we have a universe that apparently required this specific unnatural number to exist at all. This is where the conversation starts to get genuinely philosophical. Part 9. We've seen this pattern before. Before we go fully into the philosophical deep end, it's worth pausing for a moment to ask whether physics has been here before, facing an unnatural number that turned out to have an explanation, just not the one anyone expected. Because if the answer is yes, then the hierarchy problem might not be a sign that physics is broken. It might be a sign that physics is about to make one of its great leaps. And the history of the field suggests that these two things, a stubborn fine-tuning with no explanation, and a major discovery just around the corner, have a habit of showing up together. Let's go back to the 1960s. Physicists studying the weak interactions were piecing together the early framework that would eventually become the standard model, and they kept running into something that didn't quite fit. The kaon, a particle made of a strange quark bound to an up or down quark, had a mass that looked suspicious. Not the mass itself, but the difference in mass between its two neutral states. The neutral kaon comes in two versions, distinguished by how they decay, and the splitting between their masses is extraordinarily small, about 3.5 microelectron volts. To give you a sense of just how small that is, the electron, already a lightweight by particle physics standards, has a mass of about 511,000 electron volts. The kaon mass splitting is roughly 150 billion times smaller than that. It was a number that sat there in the data, looking perfectly measured and perfectly real, with no theoretical reason to be anywhere near that tiny. This was fine-tuning, not as extreme as the hierarchy problem, not 17 orders of magnitude, but fine-tuning nonetheless. The strong interactions that bound the kaon's quarks together operated at an energy scale hundreds of millions of times larger than this mass splitting. By the logic of naturalness, the splitting should have been of a similar size to the strong scale. Instead, it was negligibly small, and nobody could explain why. What happened next is one of the great detective stories in particle physics. In 1970, Sheldon Glashow, John Iliopoulos, and Luciano Maiani were working on the theory of weak interactions. They noticed that certain quantum corrections, loop diagrams involving virtual particles running inside Feynman diagram loops, were producing contributions to the kaon mass splitting that should have been large. The contributions from up quark loops and down quark loops partially cancelled, but only partially. There was a leftover piece that was still far too big. The theory, as it stood with only 3 known quarks, up, down, and strange, couldn't explain the tiny observed splitting. The quantum corrections were running away. But Glashow, Iliopoulos, and Maiani realized something. If there were a 4th quark, one with a specific set of properties, coupling to the weak force in a particular way, then its loops would cancel the remaining contribution almost completely. The cancellation wouldn't be accidental. It would be enforced by the structure of the theory. The 2 sets of corrections from the existing quarks and from the new hypothetical quark would nearly cancel because of how the weak interaction couples to quark pairs. Make the cancellation complete, the kaon mass splitting becomes naturally small, not fine-tuned, natural. They called their proposal the Jim mechanism, and it required a 4th quark. They called it the charm quark, and they predicted a rough mass range for it based on how complete the cancellation needed to be to match the observed kaon splitting. 4 years later, in November 1974, 2 independent experiments, one at Brookhaven National Laboratory and one at the Stanford Linear Accelerator Center, simultaneously announced the discovery of a new particle. They called it the J and the PSI respectively, and it immediately became known as the JPSI. It was a bound state of a charm quark and a charm antiquark. The charm quark was real. It had a mass of about 1,500 million electron volts, right in the range the Jim calculation had suggested. What had looked like fine-tuning was actually a signpost. It was the equations telling physicists quietly but insistently that something was missing, that the theory was incomplete, that a new particle existed at a scale just beyond what the experiments of the time could reach. And when the technology caught up, the particle was right there, exactly where the fine-tuning had predicted it would be. This is the template that gives physicists hope about the hierarchy problem. The logic runs like this. The Higgs mass looks fine-tuned. The standard model, taken by itself, can't explain why it's small. That fine-tuning might be a signpost, just like the kaon splitting was a signpost, pointing at particles or structures that exist at a scale just beyond current experimental reach. Something analogous to the charm quark, but for the Higgs. Something whose loops, when added to the theory, make the cancellation natural rather than coincidental. Supersymmetry was supposed to be that something, of course, and the LHC's failure to find it has dimmed that particular light. But the kaon story doesn't require that the first proposed explanation is the right one. What it requires is that fine-tuning be taken seriously as evidence of incompleteness. Glashow, Iliopoulos, and Maiani didn't find the charm quark by luck. They found it by taking a fine-tuning problem seriously enough to ask what hidden structure would resolve it, and then following the mathematics to its conclusion. The question now is whether someone, somewhere, is doing the same calculation for the Higgs, and whether the next generation of machines will give them the experimental confirmation. The Future Circular Collider is the most ambitious proposal currently on the table. It would be built at CERN, using some of the existing tunnel infrastructure, but requiring a new tunnel ring with a circumference of about 91 kilometers. That's more than 3 times the LHC's 27-kilometer ring. In its first phase, it would operate as an electron-positron collider, producing Higgs bosons by the millions under clean, controlled conditions. A Higgs factory, allowing precision measurements of the Higgs couplings to fractions of a percent. Any deviation from standard model predictions in those couplings would be a sign of new physics. In its second phase, it would transition to proton-proton collisions at center of mass energies up to 100 trillion electron volts, about 12 times the LHC's current reach. Meanwhile, in China, the Circular Electron-Positron Collider is being seriously planned, with similar ambitions for a Higgs factory phase and a potential upgrade to a high-energy proton collider. These projects are not science fiction. They are engineering proposals with cost estimates and timeline discussions and political negotiations happening right now. If any of these machines is built and reaches its design energy, it will probe territory that the LHC could never reach. New particles, new interactions, new structures. If they exist at the TeV scale or above, these colliders have a chance of finding them. And if they find something that makes the hierarchy problem dissolve, some new symmetry, some composite structure, some unexpected cancellation mechanism, it would be one of the most significant moments in the history of physics. The confirmation that fine-tuning was, once again, a signpost. But here is where intellectual honesty requires a harder look at the analogy. The kaon mass splitting was fine-tuned by a few orders of magnitude. The charm quark that resolved it was sitting at an energy scale just barely out of reach of the experiments that found the problem. The gap between the problem and the solution was modest. You needed to push a little further, build a slightly more powerful machine, and the answer was there. The hierarchy problem is fine-tuned by 17 orders of magnitude. If the resolving physics is analogous, if it's hiding just one step beyond current reach, then the FCC should find it. But there's no guarantee that the resolving physics is just one step away. The very severity of the fine-tuning might mean that the relevant scale is not at 100 trillion electron volts, but at 1,000 trillion, or 1,000,000 trillion. It might be at an energy we will never be able to probe directly with any collider built on Earth, no matter how large. The kaon analogy is encouraging. It is not a proof, and there's a deeper disanalogy worth sitting with. The charm quark resolved the kaon fine-tuning by providing a new loop diagram that completed a near cancellation. The mechanism was clear, calculable, and testable. Whatever resolves the hierarchy problem, if something does, will need to deal with a cancellation across 17 orders of magnitude. That requires something structural, not just a new particle. It requires a symmetry, or a compositeness, or a dynamical mechanism, or something we haven't thought of yet, that enforces the cancellation at a deep level. The analogy to the charm quark is suggestive of the pattern. It doesn't tell you the scale. It doesn't tell you the mechanism. It doesn't tell you whether the answer is experimental or theoretical or something else entirely. What it does tell you is that fine-tuning has been wrong before, that the equations have hidden structure before, that following an unnatural number to its logical conclusion has led to genuine discovery before. Physics has been here, in a sense, standing in front of a number that seemed to violate everything it knew about how parameters should behave, with no theory to explain it, and eventually finding the answer in a place it hadn't thought to look yet. Whether the hierarchy problem ends the same way, nobody can say. But the Kaon story is a reason, not a certainty, but a real reason, to believe that the screaming in the equations might be pointing somewhere, and that somewhere might have a name we just haven't written down yet. Part 10. Or there is no answer. What if the Higgs mass isn't fine-tuned because a mechanism enforces it? What if it's fine-tuned because only universes with fine-tuned Higgs masses can produce observers? What if the 17 decimal places of cancellation aren't waiting for an explanation, because they're not the kind of thing that gets explained? This is the anthropic argument, and it is either the most profound insight in modern physics or the most dangerous abdication of scientific ambition, depending on who you ask. There is no polite middle ground here. Physicists who take this idea seriously and physicists who find it repellent are not really disagreeing about the math. They're disagreeing about what science is for, about what counts as an answer, about whether we're here because the conditions allow it is a satisfying place to stop. Let's lay it out carefully, because it deserves more than the dismissive treatment it sometimes gets in popular discussions, and also more than the uncritical enthusiasm it sometimes receives from people who find the multiverse romantically appealing. The anthropic principle, in its most careful formulation, says that observations about the universe are necessarily conditioned on the existence of observers to make those observations. Read that slowly, because it sounds trivially obvious, and yet has enormous consequences. You can only observe a universe that permits your existence. You cannot observe a universe in which you don't exist because you don't exist in it to do the observing. This sounds like a tautology, and in a single universe picture it essentially is. Of course, we live in a universe compatible with life. We're alive. What else would we find? But the statement becomes genuinely non-trivial the moment you combine it with the possibility that our universe is not unique. If there is a vast collection of universes, each with different values of the fundamental constants, different particle masses, different force strengths, then the fact that we find ourselves in a universe where the Higgs mass is compatible with structure and life is not a coincidence requiring explanation. It's a selection effect. We're in this universe with this Higgs mass for the same reason you find yourself on a planet with liquid water and breathable air. Not because all planets are like this. Most aren't. But because the kind of entity that asks the question can only exist on the kind of planet that permits it. This collection of universes goes by several names: the multiverse, the cosmological landscape, the string landscape, and the physical mechanism most commonly invoked to produce it is called eternal inflation. Here is how eternal inflation works. The inflationary epoch, the period of extremely rapid exponential expansion in the very early universe, is, in the standard picture, a temporary phase. Inflation begins, the universe expands at a staggering rate, and then inflation ends and the universe transitions to normal expansion, reheating into the hot plasma of the Big Bang. But in eternal inflation, the inflationary phase never fully ends everywhere. Quantum fluctuations in the inflaton field, the field driving inflation, cause some regions to stop inflating while others keep going. The regions that stop inflating become bubble universes like ours, expanding into their own histories of stars and galaxies and possibly observers. The regions that keep inflating expand even faster, constantly nucleating new bubble universes in an endless, self-reproducing process. From the outside, if an outside even makes sense, the structure is fractal and eternal, a foam of bubble universes embedded in an ever-inflating background, each bubble potentially having different physical laws, different particle content, a different Higgs mass. String theory, currently the most developed candidate for a theory of quantum gravity, appears to support this picture in a specific and striking way. The equations of string theory admit an enormous number of stable or metastable vacuum configurations, different ways the extra dimensions of string theory can be compactified and stabilized, each producing a different four-dimensional physics at low energies. The estimates for how many such configurations exist range from 10 to the power of 500 to 10 to the power of 1000. These are not precise numbers. They depend on assumptions about string theory that are not fully resolved, but they convey the scale. Not millions of possible universes, not billions, not trillions. 10 to the 500. The space of all these vacuum configurations is called the string landscape, and if eternal inflation populates all or many of them, then the landscape becomes a physical reality rather than a mathematical curiosity. In this picture, asking, why does the Higgs have this mass, is like asking, why does Earth orbit at this distance from the Sun? It's not a question about a fundamental law. It's a question about which particular environment you happen to inhabit. And the answer is, you're here because this environment permits your existence, and that's genuinely all there is to say. Now, you might feel that this is deeply unsatisfying, and many physicists do. But before we get to the objections, it's worth spending a moment on the most striking piece of evidence in the argument's favour because it's real and it's important. In 1987, before the accelerating expansion of the universe had been measured, before there was any direct observational evidence for a non-zero cosmological constant, Steven Weinberg published a paper applying anthropic reasoning to the cosmological constant problem. The cosmological constant is the energy density of the vacuum, and as we touched on earlier, quantum field theory predicts it should be enormous while the observed value is nearly zero. Weinberg asked, if there is a landscape of possible cosmological constant values, what values would observers like us be able to measure? His reasoning was this. If the cosmological constant is too large and positive, the universe expands so fast that matter never has time to clump together. Galaxies never form. No galaxies means no stars. No stars means no heavy elements. No heavy elements means no chemistry and no biology. Observers cannot exist in a universe with a cosmological constant, much larger than what's needed to just barely permit galaxy formation. Using this anthropic selection criterion, Weinberg derived a rough upper bound on the cosmological constant. It should be small enough to permit galaxy formation, but not necessarily zero. He predicted it would be non-zero, small but positive. 11 years later, in 1998, two independent teams studying distant supernovae, the Higgs Supernova Search Team and the Supernova Cosmology Project, discovered that the universe's expansion is accelerating. The cosmological constant is non-zero. It is small and positive. It sits in exactly the range Weinberg's anthropic argument had predicted. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 for this discovery. That is not nothing. That is a genuine theoretical prediction made before the measurement, using anthropic reasoning, that turned out to be correct. You can argue about whether it was truly predictive or whether the range was broad enough to constitute a lucky guess. But it happened. The anthropic argument worked, at least once, in a way that led to a real prediction that was later confirmed. Could it work for the Higgs mass too? This is where the argument gets murkier, and where the analogy to the cosmological constant starts to strain. The anthropic criterion for the cosmological constant is relatively clean. Galaxies either form or they don't. That's a sharp threshold, you can calculate it. Below a certain cosmological constant, galaxies form. Above it, they don't. The anthropic window is well defined. For the Higgs mass, the criterion is significantly less clean. How much variation in the Higgs mass would actually be lethal to observers? Physicists have studied this carefully, and the results are genuinely uncertain. Some analyses find that if the Higgs mass were, say, 10 times larger, the quark masses would increase proportionally, and the proton and neutron masses would shift enough to destabilize the chemistry of atomic nuclei. Hydrogen wouldn't burn stably in stars. Carbon wouldn't form in stellar nucleosynthesis. The anthropic window would be tight. Other analyses are more permissive. They find that even with a Higgs mass several orders of magnitude different from ours, some form of complex chemistry might still be possible, though not necessarily our kind. The boundary of the habitable zone in Higgs mass space is not sharp the way the cosmological constant boundary is, and a fuzzy anthropic window is much harder to use as a predictive tool, so the anthropic argument for the Higgs mass is weaker than for the cosmological constant. More contested, more dependent on exactly what you mean by observer and compatible with life. It can't be straightforwardly ruled out, but it can't be straightforwardly confirmed either. And then there's the deeper objection, the one that isn't about the details of the calculation, but about the whole framework. Physics, since Galileo and Newton, has been in the business of finding laws, not just descriptions, laws, precise mathematical relationships that tell you why things are the way they are, in a way that lets you predict what you haven't yet measured. Newton didn't just describe how planets move. He derived it from a force law that also described falling apples and cannonball trajectories in the tides. Maxwell didn't just catalogue electromagnetic phenomena, he unified them in 4 equations that predicted radio waves before anyone had ever generated one. Dirac didn't just note that electrons had spin, his equation required the existence of antimatter, which was then discovered. The anthropic argument is not a law in this sense. It doesn't give you a calculation. It doesn't produce a number you can compare to a measurement. It says, we're here because the Higgs mass is compatible with our existence. That's technically true. The way we're alive because we haven't died yet is technically true. It's not wrong. It's just not what physics has traditionally meant by an explanation. When we say natural selection explains the complexity of life, we mean something specific. There is a mechanism, variation, inheritance, differential reproduction, whose operation we can describe in detail, observe directly, model mathematically, and use to make predictions about populations that haven't been studied yet. The explanation has content. The anthropic argument, applied to the Higgs mass, has the structure of an explanation without the content. It tells you the outcome. We exist, therefore the Higgs mass is compatible with existence. But it doesn't tell you the mechanism that produced this particular vacuum, this particular bubble universe, this particular Higgs mass, out of the landscape of possibilities. Many physicists feel that accepting anthropics as a final answer is giving up, that it converts physics from a discipline that explains why the universe is the way it is, into a discipline that observes that the universe is the way it is because we're in it, that it removes the hierarchy problem from the category of puzzles to be solved and puts it in the category of facts to be accepted, and that this is a category error, a philosophical retreat dressed up as a scientific conclusion. Others push back hard on this. The string landscape and eternal inflation are not metaphysical hand-waving. They have mathematical content. The string landscape arises from real calculations in string theory. Eternal inflation arises from real inflationary cosmology. These are scientific proposals with specific implications, and the failure of supersymmetry at the LHC, the non-appearance of the particles that were supposed to make naturalness work, is actually exactly what you'd predict if the anthropic picture is correct and naturalness is a misleading guide. If the hierarchy problem has an anthropic resolution, you would expect the LHC to find the Higgs, but not the superpartners, which is precisely what happened. That's not proof, but it's not nothing either. The debate is real, live, and unresolved. It runs to the deepest questions about what science is actually for. Is physics in the business of explaining why constants have the values they do? Or is it acceptable to explain some values by reference to observer selection, the way we explain why we live on a planet with liquid water, not by a unique law of planetary formation, but by noting that the alternative planets don't have anyone on them to wonder about it? Nobody has won this argument, and the answer may not come from philosophy at all. It may come from experiment, from whether the next generation of colliders finds the particles that would make naturalness work, or whether the particle physics landscape continues to look exactly like a finely tuned standard model, with no new physics anywhere in sight. If the FCC runs and finds nothing at 100 trillion electron volts, the case for the anthropic resolution becomes significantly harder to resist. But here is the thing about the hierarchy problem that makes it unlike almost any other open question in physics. It is not alone. There is a companion problem sitting right alongside it, so extreme that it makes the hierarchy problem look like a minor rounding discrepancy. And its existence, the fact that we have not one but at least 2 of these impossibly fine-tuned numbers in the foundations of physics, suggests that something deeper is going on, something structural, something that might point not toward a missing particle or a selection effect, but toward a gap in the entire framework we've been using to describe reality. That companion problem has a number at its center, and that number has 122 zeros. Part 11. The pattern of impossible numbers. The cosmological constant is the energy density of empty space, and I want you to hold that phrase for a moment. The energy density of empty space, because it already contains something strange. Empty space, by the intuition most of us carry around, should have no energy. It's empty. That's what empty means. But quantum field theory disagrees, and it disagrees loudly. We've spent a lot of this conversation talking about virtual particles, the ceaseless churning of particle-antiparticle pairs popping in and out of existence in the quantum vacuum, too brief to observe directly but absolutely real in their collective effects. Every quantum field contributes to this activity. The electron field fluctuates, the quark fields fluctuate, the Higgs field fluctuates. Even the gravitational field at the quantum level should contribute. All of these fluctuations carry energy, and when you add up all of that zero-point energy, the irreducible minimum energy that quantum mechanics assigns to every field even in its ground state, you get a contribution to the energy density of empty space, a cosmological constant, a number. The question is, what number? When you do the calculation in quantum field theory, integrating the vacuum energy contributions up to some cutoff scale, the answer you get is roughly 1 in what physicists call Planck units. Planck units are the natural units of quantum gravity. They're built from the speed of light, Newton's gravitational constant, and Planck's constant, combined in the unique way that produces units of energy, length, and time. In these units, the Planck energy is about 1.2 times 10 to the 19 billion electron volts, and the naive quantum field theory prediction for the vacuum energy density is of order 1 in those units, not 10 to the minus 10, not 10 to the minus 50. 1, the maximum natural value, the scale where gravity and quantum mechanics meet. Now here is the measurement. The observed value of the cosmological constant, determined from the accelerating expansion of the universe, first confirmed in 1998 by those supernova observations we discussed, is approximately 10 to the power of minus 122 in Planck units. A tiny, almost inconceivably small positive number, non-zero, that's important, and that's what those observations confirmed, but so close to zero that the difference between it and zero is essentially invisible on any scale a human can intuitively grasp. The ratio between the theoretical prediction and the observed value is 10 to the 122. I want you to actually sit with that number for a moment, because I think it deserves more than a quick read. 10 to the 122, 1 followed by 122 zeros. If you started writing that number out by hand and wrote 1 digit per second, without stopping to eat or sleep, it would take you about 4 minutes. 4 minutes to write a number that represents the mismatch between what our best theory predicts and what the universe actually does. The hierarchy problem, the fine-tuning of the Higgs mass, the crisis we've been building toward this entire video, has a mismatch of 10 to the 17, 17 orders of magnitude. We've spent a long time establishing why that's considered catastrophic for theoretical physics, why it drives physicists to propose supersymmetry and extra dimensions and anthropic landscapes, why it suggests the standard model is fundamentally incomplete. The cosmological constant problem is 7 times worse, in orders of magnitude, 122 versus 17. The hierarchy problem, next to the cosmological constant problem, starts to look almost reasonable, almost like a rounding error that got a little out of hand. This is the most extreme fine-tuning problem in all of physics, by a wide margin, and unlike the hierarchy problem, which at least has proposed solutions that are testable in principle, supersymmetry, composite Higgs, extra dimensions, the cosmological constant problem has no compelling solution at all. The anthropic argument works reasonably well here, as we discussed in the last section. Weinberg's 1987 prediction was a real success, but even the anthropic argument doesn't explain the mechanism. It doesn't tell you why the vacuum energy contributions, which should be of order 1 in Planck units, are somehow cancelling to leave behind a residue of 10 to the minus 122. It just tells you that if they didn't cancel to that degree, galaxies wouldn't form and we wouldn't be here to measure it. Modified gravity theories, proposals where Einstein's general relativity is replaced by a more complicated gravitational theory at large scales, can shift the cosmological constant problem around, change its apparent severity, reframe where it lives in the mathematics, but they don't obviously solve it. You push the fine-tuning from one place to another. The problem is stubborn. It doesn't dissolve, it relocates. String theory, which is supposed to be the framework that reconciles quantum mechanics and gravity, has a complicated relationship with the cosmological constant problem. The string landscape has an astronomical number of vacuum configurations, and many of them have cosmological constants that are not catastrophically large. The anthropic argument becomes more plausible in the landscape picture. There are enough vacua with small cosmological constants that selecting for observer-compatible universes might naturally land you in one. But this is not a calculation. It's a plausibility argument, and it requires accepting the whole landscape and multiverse picture with all its philosophical baggage. The cosmological constant sits there, 10 to the minus 122 in Planck units, the most extreme fine-tuning in science, with no agreed-upon resolution and no experimental path to testing the proposed explanations. Now, let's bring in the third member of this family of puzzles, because I think seeing all three together changes how you think about any one of them. Gravity is the weakest force in nature, embarrassingly, absurdly, almost comically weak compared to everything else. Consider two protons sitting next to each other in a nucleus. Between them act four forces. The strong nuclear force holds their constituent quarks together, and indirectly, binds them to their neighbours. The weak nuclear force is responsible for certain radioactive decays. The electromagnetic force, since protons are both positively charged, pushes them apart, and gravity pulls them together. Now compare the last two. The electromagnetic repulsion between two protons is roughly 10 to the 36 times stronger than the gravitational attraction, 36 orders of magnitude. Gravity is not merely weaker than electromagnetism in the way that, say, a gentle breeze is weaker than a hurricane. It's weaker in a way that puts it in a completely different conceptual category. If electromagnetism were a skyscraper, gravity at the particle scale would be a bacterium sitting on the pavement, somewhere in the vicinity of that skyscraper's shadow. We experience gravity as significant only because it's cumulative. Every atom in the Earth pulls on every atom in your body. 6 times 10 to the 24 kilograms of rock and iron and water, all pulling together, and that's why you feel pinned to the ground. But at the level of individual particles, gravity is so feeble that no particle physics experiment has ever detected a gravitational interaction between subatomic particles. We've measured everything else about particle interactions to extraordinary precision. Gravity between particles might as well not exist for all the difference it makes in those experiments. Why is gravity so weak? The answer, when you trace it through the mathematics, brings you right back to the hierarchy problem. The strength of gravity is set by Newton's gravitational constant g. In particle physics units, g is proportional to 1 divided by the Planck mass squared. The Planck mass is about 1.2 times 10 to the 19 billion electron volts, the energy scale at which gravity and quantum mechanics become comparably important. Now compare that to the electroweak scale, the scale of the W and Z boson masses, which is set by the Higgs field's vacuum expectation value, at about 246 billion electron volts, or roughly 10 to the 2 billion electron volts. The ratio between the Planck scale and the electroweak scale is about 10 to the 17, which is exactly the ratio that defines the hierarchy problem. The hierarchy problem asks, why is the Higgs mass so much smaller than the Planck scale? The weakness of gravity asks, why is gravitational interaction so much weaker than electroweak interaction? These are not two separate questions. They are the same question, written in two different notations. The weakness of gravity is the physical manifestation of the hierarchy problem. The hierarchy problem is the theoretical statement of why gravity is weak. They're two faces of the same coin, and that coin has been sitting on the table of physics for 50 years with no one able to pick it up. So now step back and look at the full picture. 3 problems. The hierarchy problem, fine-tuning of 10 to the 17. The cosmological constant problem, fine-tuning of 10 to the 122. The weakness of gravity, which is the hierarchy problem restated. All 3 involve extreme separations between physical scales. All 3 involve numbers that sit at values many orders of magnitude smaller than theoretical expectations. All 3 defy the naturalness principle. And all 3 remain unsolved. Is that a coincidence? 3 separate fine-tuning crises in physics, all of the same general character, arising from the same theoretical framework. The instinct of most working physicists when they see a pattern like this is that it probably isn't coincidence. When the same kind of problem shows up in multiple places, it usually means there's something wrong with the framework itself. something systematic that the framework is doing incorrectly, which produces these apparent fine-tunings as symptoms. Find the flaw in the framework, and the fine-tunings dissolve together. What could that flaw be? There are a few candidates, none of them conclusive. One possibility is that naturalness itself is the wrong guide, and we've been misled by it. Naturalness is an intuition developed from studying physics at energy scales accessible to human experiments. The Standard Model, general relativity, the great successes of 20th century physics, they were all built in an energy range stretching from everyday scales up to the TV scale. Maybe naturalness is a good guide in that regime but breaks down at the scales relevant to the cosmological constant and the Planck mass. Maybe our intuition about what parameters should look like is simply calibrated wrong for the deepest levels of the theory. This is a coherent position. It's uncomfortable, because it removes one of the main tools physicists use to guide theory development. But discomfort isn't a refutation. Another possibility is that all three problems are connected, that they're different symptoms of a single missing piece in our understanding of the vacuum. The cosmological constant problem and the hierarchy problem both involve the quantum vacuum in essential ways. The cosmological constant is literally the energy of the vacuum. The hierarchy problem arises because the Higgs mass is sensitive to virtual fluctuations of the vacuum. Gravity in general relativity couples to energy density, including vacuum energy. There may be a deep sense in which all three problems are asking the same question about how the vacuum works at the quantum gravitational level, and we're failing to answer it because we don't yet have a consistent theory of quantum gravity. Several approaches to quantum gravity suggest that the relationship between the Planck scale and the electroweak scale is not accidental. In some models of large extra dimensions, the apparent hierarchy between the two scales arises because gravity propagates through more dimensions than the other forces, diluting its strength in the 4 dimensions we observe. In these models, the true Planck scale might be close to the electroweak scale, and the hierarchy problem dissolves geometrically. These models have been searched for at the LHC and not found, but they illustrate the general idea that the hierarchy might be an artifact of our limited perspective, a 4-dimensional projection of a higher dimensional reality where things are more natural. There is one thing that distinguishes the hierarchy problem from its companions in this family of fine-tuning puzzles, and it's worth emphasizing because it matters enormously for the future of the field. The Higgs mass is testable. The cosmological constant problem lives at the intersection of quantum field theory and gravity, a regime we don't have a consistent theoretical framework for, and one that's essentially impossible to probe directly in experiments. The weakness of gravity at the particle scale is measured but can't be easily manipulated. But the Higgs boson is a particle. You can produce it in a collider. You can measure its mass, its spin, its couplings to every particle it interacts with. Any new physics that explains the hierarchy problem, any symmetry, any compositeness, any dynamical mechanism, will necessarily affect how the Higgs couples to other particles. It will leave footprints, measurable, specific, falsifiable footprints. The precision measurements of Higgs couplings at the LHC, and even more so at future Higgs factories like the proposed FCCE or CEPC, will push those coupling measurements to fractions of a percent. If the Higgs is composite, a bound state of more fundamental constituents, its couplings will deviate from standard model predictions in a specific, calculable way. If there are heavy particles mixing with the Higgs, they'll shift the couplings. If supersymmetric partners exist at any scale that affects the Higgs sector, they'll leave traces. The Higgs is the most sensitive probe we have of the physics that might resolve the hierarchy problem. And we're still measuring it, still pushing the precision, still looking. The cosmological constant problem may require a revolution in quantum gravity to understand. The weakness of gravity may not yield its secrets until we have a full theory of quantum spacetime. But the hierarchy problem, the particular fine-tuning at the center of this whole story, is within our experimental reach. The Higgs boson is sitting there at 125 billion electron volts, accessible, measurable, couplings slowly being pinned down to higher and higher precision. If there is an answer, the Higgs will know it. We just have to keep asking. Part 12. The particle that finished physics and broke it. The Standard Model of particle physics is, by any reasonable measure, the greatest scientific achievement of the 20th century. It describes all known matter and all fundamental forces except gravity, with a precision that is, in some cases, better than 1 part in a billion. The magnetic moment of the electron, a measure of how the electron interacts with a magnetic field, has been calculated from the Standard Model and measured experimentally to 12 significant figures, with theory and experiment agreeing to within experimental error. 12 decimal places of agreement between theory and experiment, sustained over decades of increasingly precise measurements. The Standard Model predicted the existence of the W and Z bosons before they were discovered and got their masses right. It predicted the existence and properties of the charm quark, the bottom quark, and the top quark before each was found. It predicted gluon jets before they were observed. It predicted the existence of the Higgs boson 50 years before the LHC found it. It is not an approximation or a model in the casual sense of the word. It is an extraordinarily precise mathematical framework that describes, as far as we can tell, the complete catalogue of fundamental particles and forces that make up everything we've ever observed directly. And yet, the Standard Model has problems. Not problems in the sense of it predicts wrong things. It doesn't. It predicts the right things with extraordinary accuracy. The problems are in the sense of it doesn't tell us why. Why are there 3 generations of quarks and leptons? Why is the top quark so much heavier than the electron? Why are the force coupling constants the values they are? Why is the Higgs mass what it is? The Standard Model doesn't answer these questions. It describes. It doesn't explain. The hierarchy problem is the most extreme version of this explanatory gap. And the discovery of the Higgs boson, the event that completed the Standard Model, that filled in its last missing piece, that gave physicists the full picture they'd been building toward for 50 years, also made the hierarchy problem undeniable. Before July 4th, 2012, you could tell yourself that the Higgs might turn out to be heavy, that it might sit at the TV scale or higher, where natural theories like supersymmetry predicted it would if those theories were correct. Once the Higgs was measured at 125 billion electron volts, that hope evaporated. The Higgs is light, unnaturally, inexplicably, beautifully light. And nothing in the Standard Model explains why. Where does this leave us? There are 3 broad possibilities, and physics is right now actively wrestling with all 3. None of them is settled. None of them has clearly won. The first possibility is that new physics exists and we haven't found it yet. Not because it doesn't exist, but because it's hiding at energy scales just beyond our current reach, or in production channels we haven't fully explored, or in subtle signatures we haven't fully characterized. This is the optimistic view. The FCC and other next-generation colliders might find supersymmetric particles, or composite Higgs signatures, or extra dimensions, or some entirely unexpected structure that makes the hierarchy problem dissolve the way the kaon fine-tuning dissolved when the charm quark was found. The answer is out there. We just haven't gotten there yet. The second possibility is that the anthropic argument is right, and the Higgs mass is an environmental parameter rather than a fundamental one. Our universe is one of many, perhaps enormously many, and we're here because we're in one of the ones with a compatible Higgs mass. This view doesn't explain the fine-tuning in the traditional sense. It dissolves it, reframes it as a selection effect rather than a puzzle to be solved. It's intellectually uncomfortable for many physicists, but it may be true. The third possibility is the most radical. Our framework is wrong. Quantum field theory, the mathematical language of the Standard Model, may be incomplete in a way that makes the hierarchy problem an artifact of using the wrong language. Just as the Newtonian mechanics was not wrong so much as incomplete, valid in a certain regime, but requiring replacement by general relativity at large scales and by quantum mechanics at small ones. Quantum field theory might be a low-energy approximation of something more fundamental, something we don't yet have, and in that more fundamental theory, the question, why is the Higgs mass small, might not arise in the same form. The problem might be a symptom of our limited perspective. All 3 of these options are live. All 3 have serious proponents among serious physicists. The LHC continues to run. Future colliders are being planned. The precision measurements of the Higgs boson's properties continue to improve. Any deviation from Standard Model predictions in the Higgs coupling to fermions or gauge bosons would be a clue toward new physics. The experiments go on, but it's worth sitting with what this means for the project of fundamental physics. For most of the history of physics, each generation of physicists has been able to point to a set of open questions and say, we know the shape of what we're missing. We can see the gap in the map. We know roughly what to look for. Newton looked at planetary motion and said, gravity must follow an inverse square law. Maxwell looked at light and said, there must be a unified theory of electricity and magnetism. Einstein looked at gravity and said, space and time must be curved by mass. Dirac looked at relativistic quantum mechanics and said, there must be antiparticles. These were educated guesses about the shape of the missing piece. Right now, for the hierarchy problem, we are less certain about the shape of the missing piece than at almost any previous moment in the history of physics. We know there's a piece missing. We know roughly the scale at which it should enter, if naturalness is our guide. We've looked for the obvious candidates and haven't found them, and the three broad options, new physics, anthropics, wrong framework, are so different from each other that they imply very different futures for the field. If new physics is hiding just around the corner, physics is on the verge of one of its greatest discoveries. If the anthropic argument is right, physics has to come to terms with a new kind of explanation that doesn't fit the traditional mold. If the framework is wrong, we need a revolution, a conceptual shift as profound as quantum mechanics or general relativity, to even formulate the right questions. The Higgs boson, 125 billion electron volts sitting in its quantum field, coupling to everything that has mass, maintaining the stability of matter with its specific, improbable, unjustified value, is the best clue we have to which of these futures is the right one. We don't know yet. We don't know why the universe is alive, but let's think about what we do know and why it matters. You are made of atoms. Your atoms are made of protons and neutrons and electrons. Your protons are held together by the strong force. Your electrons orbit in quantum shells governed by electromagnetism. The chemistry that makes you alive, the carbon bonds, the water molecules, the DNA, the protein folds, the neural signals, all of it exists because the particles involved have specific masses, because those masses let atoms form and remain stable, because the electroweak symmetry broke at the right moment in the early universe and settled the Higgs field at the right value, because 125 billion electron volts is the number that came out of an extraordinary, unexplained cancellation between the bare Higgs mass and 17 orders of magnitude of quantum corrections. You are here because a number that shouldn't be small is small. Physicists look at this and see either a profound mystery that will eventually yield to human understanding, or a window into a vast landscape of universes where the question, why us, has no local answer. Either way, the Higgs boson is not just the particle that completed the Standard Model. It is the particle that revealed the Standard Model's most important limitation. It is the particle that tells us, more clearly than any other measurement, that our deepest theory of reality is beautiful and precise and astonishingly successful, and still, somehow fundamentally incomplete. The discovery of the Higgs boson in 2012 was the end of one chapter and the beginning of another. The first chapter was, does the mechanism for mass actually work? Yes. Confirmed. 5 sigma, Nobel Prize, Peter Higgs weeping in an auditorium in Geneva, 48 years after his paper. The second chapter is, why does the mechanism have the parameters it does? Why is the Higgs mass what it is? Why does the universe balance on this specific number? And that chapter, the one that matters most for our deepest understanding of reality, is still being written. The LHC runs on. The theorists calculate, the data analysts sift through petabytes of collision data, looking for anomalies, deviations, hints of something new. The planning committees debate the next great machine. The philosophers of physics argue about whether naturalness was ever the right guide. The experimentalists push the precision measurements of Higgs couplings to another decimal place, looking for the first crack in the Standard Model's perfect agreement with experiment. And the Higgs boson, indifferent to all of it, sits in the quantum vacuum at 125 billion electron volts, giving mass to everything, explaining the stability of matter, maintaining the conditions for the universe's existence, completely unexplained. The number is wrong, spectacularly, impossibly, cosmically wrong by every theoretical expectation. And yet here it is. Here we are. The Higgs boson didn't answer why the universe exists. It revealed that we don't yet know how to ask the question.